So I'd like to briefly review both statements of the fundamental theorem of calculus. Remember that there are two parts. The one that you usually use is the second part, which kind of comes from the first part. So the first fundamental theorem of calculus. And here's the story, okay? So if I have some continuous function on an interval AB, okay, and I'm out of this function, I'm going to make a new function. So this is x, this is y. So this is the graph of y equals f of x. Okay. So I'm going to make out of this a new function that I'm going to call g of t. And it's going to be defined to be the definite interval from c to t of f of x dx. So let's understand what this function is, okay? C is just some value in between a and b. And t is going to be also some value in between a and b, okay? C is fixed. We're not moving C. We just pick it, okay? As you see, it's not really going to matter which one we pick. And this is our variable. And so g of t is a function that integrates from c to t of this function f of x. So for example, let's say that c equals, is this over here, just as an example. So g of, and let's call this, I don't know, 2. I don't know. So g of 2 equals the integral from c to 2 of f of x dx. So g of 2 would just be, well, it could be represented as the area of that region over there. And so the question then becomes, so this is a pretty cool function, because as we move t, we're just going to be getting a different area, an area of a different region, right? So if I picked instead t to be 1.5, then g of 1.5 would be the area of this region over here, not the rest of it. Is that clearer, maybe? So the interesting question is, what is the rate of change of this function with respect to its only independent variable t? So in other words, what is g prime of t, or dg dt? And that's what the fundamental theorem tells us, the first fundamental theorem. So the first fundamental theorem says that g prime of t, which is of course the derivative with respect to t of the integral from c to t of f of x dx, is just simply f of t. So let's rephrase the question. If I fix c, and I vary t, what is the rate of change of the area that's accumulated between the x-axis, the line x equals t, and the line x equals t? and the graph of that. What's the rate of change of accumulation of area? Well, it's just going to be the height of the function, because because just as you vary t, the rate of change of the area is just going to be the height of the function, which should make sense because the way that the area is accumulated is through rectangles. And so if we're just to continue t along that path, right? What it means is that in 1 unit of t, we're going to have accumulated that much area. It's exactly the same thing as if I asked you, okay, I'm driving 1 mile an hour right now. So in 1 hour, if I continue at this speed, how much will I have driven? Well, I'll have driven 1 mile, right? So that's exactly what the derivative is. So here, it's a derivative, but we just put it in a different context. We put it in the context of area and accumulation, as opposed to putting it in a different context like speed and velocity and distance and stuff like that. So that's very interesting, though, because now what we have is we have a nice relationship between accumulation of change and rate of change. So that's why this is true, and that's why this makes sense. And from this, we'll follow the second fundamental theorem. And the second fundamental theorem gives a way of evaluating integrals of continuous functions. So basically, now we're on to the second fundamental theorem. So this is the first. So the second fundamental theorem of calculus basically says that if I have a definite integral, so this is not really a definite integral in the same way. It's a function, right? It's a function of t. With a definite integral, both endpoints are fixed. Both the upper and lower limit of integration are fixed. So suppose we have a definite integral from a to b of f of x dx. Then the second fundamental theorem is what says that it's just f of b minus f of a, capital F of b minus capital F of a, where f is the antiderivative. Capital F is the antiderivative of little f of x. So it's not immediately clear that this is true. It doesn't immediately make sense, because the concept, if you're given just some arbitrary function, like say distance, in a physical context, it's not really clear what the antiderivative of a distance function actually is. So I'm going to rewrite this. I'm going to rewrite the second fundamental theorem of calculus so that it makes a little bit more sense. Instead of thinking of it as some arbitrary function and its antiderivative, I'm going to think of it instead as the derivative of some function f prime of x and the original function f of x. So what this says is that the definite interval from a to b of f prime of x dx equals capital F of b minus capital F of x. And this really makes a lot more sense, because what's going on is what we have here is each little element that we're summing up is the instantaneous rate of change times an infinitesimally small number. So what we're going to have done then is we're going to kind of have accumulated just a very small amount of change, and then we add up all of those little accumulations of change, and we get the total change. What's the total change? Well, the endpoint subtracted, the terminal minus the initial endpoint. So this should make complete sense that this formula actually works. It does follow from the first depending on how you prove it. We're not going to prove it in this class, but it's certainly worth understanding why these two theorems make sense and the difference between them, and why we should care. Why it's not trivial, because it's certainly not. And we're going to be using it over and over, and especially when we start talking about things like Stokes' theorem and Green's theorem, which essentially generalize the fundamental theorem of calculus to higher dimensions. And so this will be extremely useful to us. Okay? Thank you.